All right, good morning, everyone. In this video, we're going to look at how the physical properties of our carbonyls, which we've already looked at, will affect our reactivity of those carbonyls. So again, we have both a nucleophile and an electrophile on our carbonyl compounds. We have our oxygen in that double bond, which is nucleophilic due to the electronegativity of that oxygen. And we have our carbon, which is going to be electrophilic because those electrons are pulled away by that more electronegative oxygen. Our double bond here is going to undergo addition reactions, somewhat similar to our alkene, although this nucleophilic oxygen is going to change that reactivity compared to our alkenes. So what I'm going to look at in this video is our hydration reaction. So in the hydration reaction, we're going to add water to that double bond, very similar to the way that we added water to an alkene double bond. Now we can do this under basic or acidic conditions. So if we have basic conditions, we'll have our hydroxide ion present. Right? Under basic conditions, you have a high concentration hydroxide ion in your aqueous solution. Now, as we know, a hydroxide ion is nucleophilic. So if we take that nucleophilic hydroxide ion, we can attack our carbonyl. We're attacking, of course, that electrophilic site there where we have that partial positive charge. And we're going to have our lower electron density. Now, since we already have 4 bonds at the carbon, of course, we will also have to kick out or break a bond as we attack. So we're going to break our double bond here and move those electrons up to our electronegative oxygen that wants those extra electrons. This is very similar to, of course, our carbonyl attack that we saw with our Grignard reagents reacting with carbonyls. After we attack, we'll then have our alkoxide forming. So we add on the OH from our hydroxide, and we form our alkoxide there. Now, an alkoxide, of course, is a strong base. And since we're in aqueous solutions, we have water present that we can react with. We're going to react with water in an acid-base reaction. Water will act as our acid in the presence of our strong base alkoxide. And we're going to attack that water and deprotonate it. And this will create our hydrated product, and will regenerate our base. So we added on an OH hydroxy group as well as a hydrogen to that initial carbonyl oxygen. Now, this would be under basic conditions where we have hydroxide ions present to react with our carbonyl. But since we have this both nucleophilic and electrophilic carbonyl, we can also react under acidic conditions. Let's clear this out, and we'll see what it looks like under our acidic conditions. So under acidic conditions, we'll have, of course, hydronium ions. Which are electrophilic due to that positive charge. So here, we're going to use the nucleophilic nature of our oxygen on our carbonyl. So if we take the excess electrons from our nucleophile we can attack our hydronium ion and we'll deprotonate it. We're reacting as a base here, taking a proton from our acid to create our protonated carbonyl. So we're going to have a positive formal charge on that carbonyl oxygen because we've used one of our lone pairs to react as a base with our hydronium ion here. We're also, of course, generating water as the conjugate base of our hydronium ion acid. Now, at this point, of course, once we've reacted here and added on that hydrogen and that positive charge, we've now made this molecule overall more electrophilic. So, since we're more electrophilic, now it's going to be easier for us to attack that electrophile with a nucleophile. And we happen to have a weak nucleophile here in the form of our water. So we're going to take our water as a weak nucleophile. We can attack, again, that most electrophilic site, which is our carbon. Our oxygen has that positive charge, but it can actually share that positive charge with that adjacent carbon. Again, when we make that nucleophilic attack, we're going to have to lose our double bond to make room for that new bond that's forming down there. So this would result in our carbonyl oxygen turning into a hydroxy group. And we would add on our water at the bottom of our carbonyl, attach that electrophilic carbon. Now, our water down here can get deprotonated. This acts as an acid. We have, of course, an aqueous solution with water present. So we can deprotonate that with our water. This will regenerate our acid, and it will actually generate our same hydrated product here. So whether we're using acidic or basic conditions, we get the same hydrated product in both cases. You can see we're adding water, right? We add one hydrogen attached to our electronegative oxygen, and we add our hydroxy group to that electrophilic carbon. So overall, regardless of the acidic or basic pathway, we're adding on 1 unit of water on either side of that